introduction about give you a brief introduction about core collapse supernovae, and particularly focus on the importance of neutrinos in the context of core collapse supernovae. Then I will talk about flavor evolution, and then I will talk about how flavor evolution is modified when we include collisions and advection. I will present the numerical results of these flavor evolution calculations, including collisions and advection, and then conclude. Okay, so let me first start by talking about what are core collapse supernovae. So if we have a star which is more than 8 times massive than the mass of the sun, then we begin with a star which is mostly made up of hydrogen. And as the hydrogen burns, it forms a helium core. After a while, the hydrogen in the core gets depleted, so it does not produce any energy. So the balance between the radiation pressure and the gravitational pressure which was there is no longer there, and the gravity starts to overwhelm. This makes the star contract. And as it contracts, it heats up, and that causes the helium core to start burning. And this continues until the core is made up of iron. Now, iron is the most stable element in terms of binding energy per nucleon. So because of that, we cannot synthesize heavier elements by fusion and release energy. Okay, so that is the last stage of this nuclear fusion reaction. And when that happens, after that, the core starts to collapse on its own. So the inner part of the core undergoes a homologous collapse. What that means is that if we look at the infall velocity, it is proportional to radius. Okay, so this infall of the inner core continues until nuclear densities are reached. And the outer part of the core, which is not aware of the fact that the inner core has reached nuclear densities, keeps infalling and slams onto the inner core. As that happens, there is a bounce. The infalling matter bounces back. So there is a velocity which is radially outward, as seen here, while the outer core keeps collapsing. So that the matter is infalling here. And because of that, there is this discontinuity in the velocity, which we call the shock wave. And this shock wave propagates outward, and this shock wave is supposed to blow out the outer envelope. And this is what we call supernova. But when the numerical simulations of core collapse supernovae was done, it was realized that the shock wave loses energy while traveling through the outer core because it dissociates the iron group nuclei. And because of that, the shock stalls. So to resolve this issue, neutrinos are helpful. So when it comes to core collapse supernovae, 99% of energy is released in the form of neutrinos. And all flavors of neutrinos and their antiparticles are emitted by this collapsing core. So what Bethe and Wilson proposed is that if a small fraction of this energy is deposited in the right place at the right time, then this can lead to hydrodynamical instabilities, which would revive the shock. So how much energy is deposited by neutrinos in this region of importance? And that will depend on several factors. For example, it will obviously depend on the number of neutrinos emitted. It will also depend on the energy of the neutrinos, because the cross-section of neutrinos with matter increases with energy. And also it depends on flavor, because if we look at reactions like this, This can only happen for electron type neutrinos, this and this reaction. Because if we replace this electron neutrino by a muon neutrino, this electron will have to be replaced by muon. And in supernova core, the energy of the neutrinos is not so much that a muon can be produced. So the muon equivalent of this reaction is kinematically not allowed. So because of that, the energy deposition will also depend on the flavor of neutrinos. But the flavor of the neutrino can change, right? So how do we calculate what happens actually if we take into account neutrino flavor evolution? In order to understand that, we have to first look at how we can take into account neutrino flavor evolution. In order to do that, we can represent the neutrino flavor state by a 2x2 density matrix in the two flavor approximation. So what do I mean by two flavor approximation? By that, I mean that this X flavor is a combination of mu neutrino and tau neutrino. And so instead of a 3x3 density matrix, which should be there, I only have a 2x2 density matrix. And this density matrix evolves according to this Heisenberg equation. And the Hamiltonian, which governs the temporal evolution, has three components: the vacuum term, the matter term, and this neutrino-neutrino self-interaction term. So the vacuum term is quite simple. It only depends on the mass square difference, energy, and the mixing angle. So once we know the mass square difference and energy, we know the vacuum frequency, and mixing angle is something we can measure. And in the region of supernova region of interest, as far as supernova is concerned, the matter Hamiltonian is not that important. So throughout this talk, I will just ignore this. But what about the third term, the neutrino-neutrino self-interaction? So what do I mean by neutrino-neutrino self-interaction? By that, I mean when we look at a particular neutrino traveling in a particular direction, it experiences a refractive index due to other neutrinos in the medium. Now, this potential experienced by a neutrino depends on the flavor of other neutrinos. As we see, the Hamiltonian depends on the flavor state of the neutrino. Because of this, the equations of motion are nonlinear in nature. And also, the Hamiltonian depends on the direction of the neutrino we are considering and the direction of the neutrinos in the medium. So this makes solving the equations quite difficult. So if we look at this equations of motion that include neutrino self-interactions, there are broadly two kinds of flavor evolutions. These are called slow and fast. Now, slow flavor oscillations, collective oscillations, occur when the self-interaction potential is more or less of the same order as the vacuum frequency. And a fast flavor evolution, as the name suggests, is fast and can happen at very high neutrino number densities. At least that is the current understanding, right? And the fast flavor evolution requires something called the ELN crossing. So I will explain what this ELN crossing is. If we look at the angular distribution of neutrinos, then if this is just an illustration of what an ELN crossing is. If we look at the angular distributions of nu E and nu E bar, at this point, you will see that there is a crossing between nu E and nu E bar. And this is called the ELN crossing. And if we calculate the neutrino flavor evolution for this particular angular distribution, what we'll see is that there is a lot of flavor transformation which starts in the region of crossing, at least in the azimuthally symmetric case. But if we add to this collisions, then you can have an enhancement of flavor convergence. at least in the homogeneous case, and that was shown in this paper, which came out more than a year ago. So in this paper, what we showed is that if we start with a particular angular distribution in a homogeneous gas, then collisions can lead to an enhancement of neutrino flavor convergence. But this is not the right thing to do, because if we know what the collision term is, we cannot assume a particular angular distribution. The angular distribution has to be determined by the collision term. And that is what we did in this work, and I'll present the results for that case. But before I do that, I just want to talk about the advection term and the collision term first. And before I show you the equations of motion, I want to explain the geometry. So the geometry is spherically symmetric. So here I have drawn two spheres with radius R1 and R2. And this bold black line is the trajectory, which is a straight line. Now, if we look at these 2 points, although this is a straight trajectory, the angle with respect to the radial direction has changed. So, and this is an effect of advection in the spherical geometry. Or in other words, if we look at two neutrinos with the same radial direction but at different radii, that does not represent the trajectory. So we have to take this into account. So if we take this into account, the equation of motion looks something like this. So let me explain each of the terms. So this left-hand side of the equation is the total time derivative, which includes the partial time derivative and the advection term. On the right-hand side, we have the emission term, which does not depend on the neutrino number density. And we have an absorption term, which is proportional to the neutrino number density. And these two terms together form the direction changing term. So by construction, these two terms together conserve the neutrino number density. Okay, so if we solve this, what should we get? So what we get is that when the matter density is very large, the neutrinos are undergoing random walk and leading to an angular distribution that is more or less isotropic. And as neutrinos go towards region of low matter density, they will slowly escape. And different neutrinos of different flavor will decouple at different radii, or they will start free streaming at different radii. But the question we want to ask is, how is this picture modified when we take into account the fact that flavor transformations happen? Because you see, the non-electron type neutrinos decouple at the smallest radius, followed by electron antineutrinos and then electron neutrinos. And the average energy for each species is determined by the temperature at which this decoupling happens. Now, this is very difficult to reproduce in our calculations because we use a single energy approximation. So basically what we have done is assume that all neutrinos have a single energy. So in order to reproduce what we see in multi-energy simulations, what we have done is assume some collision profiles that will give the right order of magnitude for the ratios of luminosities, and the decoupling will happen in the right order. So if we do that, we get something like this. So this is an illustration of what the advection and the collision terms together do. So on the x-axis, you will see the angle with respect to the radial direction, and the y-axis is the radius. So when the radius is very small, you will see that the neutrino number density does not depend on cos theta. That means the neutrino angular distribution is isotropic. But as we go to larger and larger radii, the density keeps falling. So the neutrinos start becoming free streaming and they become forward peak. So the neutrinos are only going in the forwardish direction, and there's no neutrino going in the backward direction. So this is what the neutrino distribution should look like if there was no flavor transformation. Now, if we want to add neutrino flavor evolution, that is very challenging from a numerical point of view, because we have to evolve the neutrino flavor at each point. And because of the advective term, there is a finite difference involved. Okay, so the equations are not very easy to solve. So because of that, we had to make certain assumptions. And this is the list of the assumptions we had to make. So first and foremost, I assume a two-flavor approximation, which I already discussed. We also assume a perfect spherical symmetry and a single energy approximation. That means we assume that the neutrinos have a single energy. Also, the collision terms, which is the input parameter for us, because the collision rate changes as a function of radius for each flavor. And once that is determined, everything else is determined. We do not use some initial angular distributions. The angular distributions are determined by this collision terms. So, but because we are working in a single energy approximation, we had to use some simplified radial profiles for the collision terms. So this is the full equation of motion. This is the same as I showed before, but now I have added the flavor transformation. So what the goal of this work was to solve this full equation and solve it for long enough time that a steady state is reached. So that is the kind of configuration we would expect to see, because the time scales over which the density changes in the supernova is much slower than the time scale at which the flavor evolution happens. So we expect a steady state to be present at each time, more or less. So what happens if we just solve this full equation? So this is the kind of results we see. Now, let me explain what these plots are. So I took some collision term, the radial profile for the collision term, and solve it with and without the collision term, with and without the flavor transformation. And then calculated the difference between the two. So this bright blue region tells us the region which is affected by flavor transformation. Okay, and this is the plot for neutrinos, whereas this is the plot for antineutrinos. Now this is a bit difficult to visualize because this is a heat map. So what we can do is, if we want to look at how the number density changes as a function of radius, we can just average over the angle, and that will tell us how the new number density evolves as a function of radius. And this is what we see. So this is much easier to understand. So this dashed lines are the number densities of neutrinos if there is no flavor transformation. So this is what we would see if just the collision and the advection term was present. The solid lines are what happens when we include flavor evolution. And as you can see, for electron neutrinos, if we look at the decoupling radius, that is where the number density starts falling, that has reduced to a smaller radius. If we use some other kind of radial profile for collision term, we get some interesting results. So if you look at this plot, it's the same as before, but for a different input of collision terms as a function of radius. And you can clearly see there is a discontinuity here. And the same discontinuity can be seen if we average over the angle, and you will see this discontinuity here. Also, unlike the previous case, you don't see that nu e and nu x curves are sitting on top of each other, which means this is not reaching some kind of a depolarization or equipartition. Okay. So what is this telling us? So first and foremost, what we can see from these numerical simulations is that flavor equipartition is not a generic outcome. Also, when you see calculations of past flavor evolution in the literature, what happens is that the energy is generally ignored. But if we talk about the interplay between collisions and flavor evolution, the collisions are very energy dependent. So because of this, we have to do a multi-energy simulation in order to figure out what actually happens. So what are the implications of these calculations? So first and foremost, we see that the effective radius of neutrino decoupling changes due to flavor evolution. And as I was mentioning before, the average energy of neutrinos is determined by the temperature at which the decoupling happens. So this suggests that the average energy of neutrino for a particular species could be modified due to flavor evolution. But in order to be sure about this, we need to perform a multi-energy simulation. Also, if we are saying that the effective radius of decoupling is changing, that means the area of the supernova, which is emitting these neutrinos, has to be changed. And that can affect the neutrino luminosity. And these effects are not taken into account as far as the hydrodynamic simulations of core collapse supernovae is concerned. Also, what we see in these simulations is that there is an enhancement of flavor conversions when we include collisions and advection, which is similar to what we see in the homogeneous case. But unlike in the homogeneous case, it's very difficult to disentangle the effect of collisions and advection. So all we can say is that when we have collision and advection together in a spherical geometry, there is an enhancement. But we cannot tell that whether the enhancement is due to collisions or advection. Okay, so in conclusion, this puts a big question mark on the hydrodynamical simulations of core collapse supernovae, because this effect of flavor oscillations on neutrino decoupling is not taken into account. Thank you. Are there any questions?
Okay, thank you very much, Shashank. We have a
I
question.
finished in 25 minutes. Okay.
Yeah, we have a question from Evan. Evan, do you want to unmute yourself?
Should I stop the share screen or what?
I think
keep your slides up, please.
No.
Okay.
Yeah.
Okay.
Yeah.
Keep it.
Yeah.
Questions may be related to what you showed.
Okay.
Indeed. So thank you, Shashank. That was a great presentation. I just had a question kind of about the kind of the inner details of your calculation. For your emission collision term, is there a polyblocking factor that's in that, or can you just ignore it in this case?
So the thing is, polyblocking should be important, but I haven't included it because whatever is the effect of polyblocking, the error due to that will be much smaller than the error due to the fact that I'm doing a single energy calculation. So I did not want to add complications because of that. So once we do the multi-energy calculation, that will become important. So this is just to illustrate the fact that there is an interplay between the three things: the collective neutrino oscillations, collisions, and advection. What we were trying to demonstrate is just the interplay between them and not try to get a realistic neutrino emission profile, right? Because that would require a multi-energy calculation. And once we do that, polyblocking will become important. Yes.
Okay. And just to follow up on that Boltzmann-like equation that you had, you had the two integrals over the collisional function for direction changing. I mean, what are the differences between these integrals besides the dummy variable? I'm just not exactly sure what these are doing.
Okay, so basically, if you look at the term with the minus sign, okay, so minus sign is just removing neutrino in the theta direction. And this integration over cos theta prime is trivial. It's just making sure that if we integrate both of them over d cos theta, then the number of neutrinos will be the same. So this integration is just there to ensure that, okay, so let me go back, okay? So this term is just removing the neutrino in the theta direction and repopulating in some other direction. So basically what this positive term is doing is that it is taking neutrino which was going in theta prime direction and putting it in theta direction, right? But since this is a direction changing effect, we want the total number of neutrinos to be conserved. And this integral is just to make sure that happens.
I see. Okay.
Yeah.
Are these coefficients just numbers right now? Do they depend on cosine
yeah.
theta?
So these are numbers. These are functions as a these are a function of radius only.
Okay.
Yeah, but and that is a good approximation, because the thing is the neutrino direction changing scattering is dominated by neutral current scattering of nuclei, and since nucleons or nuclei, and they are all much heavier than the energy of the neutrinos, right? So mostly the scattering is isotropic in nature. So we don't need to include the angle dependence. That is not that important.
All right. Thanks a lot, Shashank.
Yeah.
Great talk.
Thanks for the question.
Thanks. Amol also has a question. Do you want to unmute yourself, or should I read it?
I can you hear me?
Yes.
So my question is that, so in some cases where you get some kind of flavor equilibration and it makes the decoupling radii of different flavors get closer to each other, right?
Yeah.
But in those cases
so that happens no matter whether the depolarization happens or not.
Oh, okay.
The decoupling radius changes irrespective of whether depolarization happens or not.
Right.
Yeah.
So then my question is that because of this effect, are the fast flavor oscillations essentially self-limiting? Because if the decoupling radii get closer, will that make the ELN crossings vanish?
Well, now the thing is, since we are solving the whole thing self-consistently, even if
Right.
it vanishes, why does it matter? Right? I mean, this is a self-consistent calculation. So that means if the ELN crossing has vanished, it has vanished because of oscillations.
Right.
Yeah. So after it has reached some kind of a steady state, why do we care whether ELN crossings exist or not, right?
No, so then I guess a way to frame my question is that, so these are like fast flavor oscillations that are happening inside the decoupling region. And then you solve them self-consistently, and then the decoupling regions get close to each other. But then once you go outside the decoupling region, does that mean that you're not getting fast flavor oscillations there, or maybe like the strength is reduced or something like that?
So I'm solving it at all radii simultaneously in a self-consistent manner.
Right.
Yeah, so all of those effects are taken into account simultaneously. Yeah. So that is actually a very good question. So it's not that I solved for each radius independently. All the radii have to be evolved simultaneously for this effect to be seen. Yeah.
Okay.
Yeah.
Okay. We have another question from Sway. If you can unmute yourself.
Yeah. Thanks very much for your talk. I have two questions. The first is is short. What's the resolution you use for the radii and angle?
Yep. It is a grid of 150 by 150 bins.
150.
150 by 150. And okay. We can verify that it is convergent. Yeah.
Okay. So you have the convergence test for that.
Yeah.
Okay. Great.
I mean convergence in the sense that just increasing the number of bins and results not changing, not anything fancy mathematical thing. Yeah.
Yeah. Okay. And the second question is about the matter terms. Yeah. So I remember you mentioned that you think the matter term is not important, so it can be ignored.
Yeah.
I can understand that in those local simulations, because ultimately even if we add matter terms, it will contribute a homogeneous phase shift for every radius. But now you are considering an inhomogeneous case.
Yep.
Is there any reason you can also still ignore it?
I mean, the justification for that is that if we run the simulation for, so in the homogeneous case, what happens is that the effect of the matter term is to reduce the effective mixing angle, right? So if we have an inhomogeneous case, what we can do is try to figure out how sensitive the simulation is to the mixing angle we use. So if the simulation is not sensitive to the vacuum mixing angle, then I would say that this is a good enough approximation, and we did that. So if we run the simulation with different values of theta vacuum, it leads to the same results. So in that, it's not as foolproof as you would want it to be, but I think it's pretty good justification.
Okay, thanks.
I don't see more questions. Oh, okay, I see. Alex has a question. Can you unmute yourself?
I have a quick question, Shashank.
Yep.
Can you summarize the degrees of freedom that have been dropped and the degrees of freedom that remain? You have a slide, but I just want to understand it a little better.
Yeah, so basically the thing is that we have a two-flavor approximation. So I've dropped one of the neutrino flavors. Then I have spherical symmetry. So because of that, there are only 2 degrees of freedom as far as the neutrino trajectory is concerned, that is R and theta. So the point on the sphere at which the neutrino is emitted, that is not relevant, right? And also the azimuthal symmetry is imposed when we consider spherical symmetry. And then I have single energy approximation. So if we just remove the single energy approximation, then it will be a full spherically symmetric calculation. So this is more or less like the bulb model, except for the fact that the radius of decoupling is not the same for all flavors, and collision terms are included. Does that answer your question? Or
yeah, I think it does. So you could have used the bulb model notation, right, where you choose angles defined at some fixed radius.
No, we can't do that, right? Because
you could, you could.
No,
okay.
because
I think you could.
No, you could not, because there are neutrinos going in the backward direction at large radius, and for that there is no emission angle.
Well, you could label those angles by something else. Are they important, by the way? This is interesting. Are they important for the calculation? I mean, this is the Halo paper that we wrote a long time with Georgian company. Was talking about these backward neutrinos. Are they important in the way your dynamics developed?
I mean, we are in the decoupling region, so there are a lot of neutrinos in the backward direction. So the formalism I've used as far as the numerical techniques are concerned, I could use those to solve the Halo problem. Yes, but I'm not sure I want to do that. But you're right that I could use the same formalism to solve the Halo problem.
And for collisions, you have both charge current and neutral current with realistic properties.
No, I do not have very realistic properties for the same reason that it's a single energy approximation. So because of the single energy approximation, it's difficult to get the right hierarchy of decoupling, because see, the decoupling happens first for nu x, then nu e bar and nu e, and that happens because so because of that, what happens is that nu e has more energy than nu e bar, right? So their collision term will be more, it has more energy when it decouples. So its collision terms will be slightly different than nu e bar. So taking that into account in the single energy approximation is difficult. So we had to basically use collision terms which reproduce the hierarchy in which the neutrino decoupling happens, rather than using it from first principles. So once we do the multi-energy calculation, then we can include the realistic terms. Does that answer your question or no?
Yeah, certainly important clarification.
Okay, thank you. We have one more question from Baha, and then we can move to discussion.
Hi, Shashank. Very nice talk. I missed something. You mentioned you do, of course, spherical symmetry assumption, but then you mentioned something about azimuthal symmetry that I missed.
All I was saying is that once we assume a spherical symmetry, azimuthal symmetry is implied, right? So if we look at the density matrix, it only depends on cos theta. It does not depend on the polar angle. It does not depend on phi.
Okay.
Right. So once a spherical symmetry is assumed, that symmetry is implied.
Okay, that's what you meant. Okay, thanks.
Okay, I don't see any more questions. So thank you, Shashank, again for this very nice talk. And
so should I stop share screen?
I will stop recording.
Okay.